The X-33 Spaceplane was one of NASA's most ambitious experimental projects of the 1990s, aiming to create a reusable spacecraft capable of reducing the cost of access to orbit. It promised technology far ahead of conventional rockets, with lifting body design and metallic composite fuel tanks that pushed engineering limits. Engineers hoped it could be a stepping stone to a fully operational single-stage-to-orbit vehicle. Its development embodied the spirit of innovation, ambition, and risk that defined a generation of space exploration. The project captured imaginations across the aerospace industry and the public alike. Early demonstrations hinted at revolutionary flight capabilities and dramatically lower operational costs. Yet, despite its promise, the X-33 never reached operational status. Its story is one of audacity, cutting-edge technology, and the harsh realities of turning bold concepts into reality. NASA conceived the X-33 in the early 1990s as a technology demonstrator for the future VentureStar single-stage-to-orbit spacecraft. The goal was to dramatically reduce launch costs by creating a reusable vehicle that could operate like an aircraft rather than a disposable rocket. Engineers designed a lifting body shape to generate lift during ascent and re-entry, rather than relying solely on rocket thrust. This approach represented a major departure from traditional vertical rocket designs. The X-33 was to be powered by advanced linear Aerospike engines, capable of maintaining efficiency at various altitudes. These engines were among the most innovative propulsion systems ever attempted. The spacecraft's fuel tanks were made from lightweight composite materials to save mass. Every aspect of the design pushed the limits of contemporary aerospace engineering. Lockheed Martin led construction, blending aerospace expertise with cutting-edge materials science. The vehicle measured roughly half the size of the intended full-scale VentureStar. Engineers built it to test technologies, aerodynamics, thermal protection, and automated flight systems. Its success would determine whether single-stage-to-orbit travel could become a reality. The lifting body shape created unique aerodynamic challenges during atmospheric flight. Control surfaces had to manage both high-speed ascent and precise landing. NASA invested heavily in computational simulations to predict behavior during flight. Pilots and engineers were entering unknown territory. By the mid-1990s, initial wind tunnel tests showed promising results. The shape minimized drag and allowed for efficient flight at hypersonic speeds. Structural components were stressed to extreme conditions. The project moved confidently into the prototype stage. Construction of the X-33 prototype began with precision machining and advanced composite fabrication. The carbon fiber-reinforced fuel tanks represented a radical innovation but introduced unknown risks. Engineers were optimistic that these lightweight tanks could withstand extreme pressure and temperature cycles. Success here was critical to validating the concept. The linear Aerospike engine underwent extensive testing on the ground. It demonstrated unique altitude-compensating thrust, maintaining performance across a wide range of flight conditions. Engineers noted early challenges with cooling and nozzle durability. These issues would later contribute to delays. Avionics and control systems were designed for near-autonomous operation. The X-33 was intended to fly with minimal pilot intervention, testing automated guidance for future spacecraft. NASA collaborated with aerospace software experts to simulate countless scenarios. The technology promised unprecedented precision in orbital maneuvers. The prototype incorporated thermal protection tiles similar to those used on the Space Shuttle. These tiles had to survive re-entry speeds without degradation. Engineers tested hundreds of combinations of materials and adhesives. This work was essential to prevent catastrophic failure during hypersonic flight. Structural tests revealed tension and stress points in the composite tanks. Engineers adjusted bonding methods and reinforcement patterns. Every modification brought new insights but also new risks. The project demanded constant innovation to remain viable. By 1996, the X-33 prototype neared readiness for atmospheric and suborbital testing. Public interest grew as NASA promised a new era of reusable spacecraft. Yet behind the scenes, technical hurdles were mounting. The next phase would prove far more challenging than anyone anticipated. Initial flight tests of the X-33 focused on atmospheric performance and landing behavior. Pilots and engineers closely monitored stability, control responsiveness, and structural integrity. Early flights demonstrated that the lifting body design could glide effectively during approach and landing. Confidence was high, but the spacecraft had yet to demonstrate orbital potential. Engine testing continued in parallel, revealing persistent problems with the linear aerospike design. Cooling and thermal stresses on engine components threatened reliability. Each test highlighted the gap between theoretical performance and real-world conditions. Engineers worked tirelessly to troubleshoot and improve the system. Composite fuel tanks were another major source of concern. Cracking and delamination appeared under pressurization cycles. NASA and Lockheed attempted various fixes, but the tanks remained fragile. These issues foreshadowed the problems that would eventually doom the program. Flight control software encountered minor anomalies during early flights. Automated guidance systems struggled with extreme flight regimes near the edges of the vehicle's envelope. Engineers revised algorithms repeatedly to maintain safety margins. Despite these setbacks, the spacecraft continued to provide valuable data. Thermal protection tiles also revealed vulnerabilities. Small fractures and attachment failures were observed after simulated reentry tests. Each observation required redesigns and reinforced assembly procedures. The cumulative effect of these challenges slowed progress significantly. By 1998, the X-33 had completed several glide tests, but key milestones remained unmet. Orbital insertion and full-scale engine operation had not been successfully demonstrated. Momentum for the project remained, but costs and delays were mounting. NASA faced a decision point about the program's future. Ultimately, the combination of structural, propulsion, and software issues raised doubts about the spacecraft's feasibility. Even minor failures threatened catastrophic loss during future orbital attempts. The program was technically impressive, but the risks were growing too great. Momentum began shifting away from X-33. As testing progressed, the X-33 program exceeded initial budget estimates. The specialized materials, engine testing, and software development demanded unprecedented resources. NASA faced scrutiny from Congress and the public over escalating costs. Questions arose about whether the program could deliver operational results. The fragile composite tanks were identified as the single most critical technical hurdle. Attempts to strengthen them often increased weight, reducing performance margins. Engineers pursued multiple approaches, but none fully resolved the problem. This uncertainty weighed heavily on decision-makers. Meanwhile, competition from other space technologies intensified. Reusable vertical rockets, derived from shuttle experience, began to appear more cost-effective. Private aerospace ventures also demonstrated smaller-scale launch capabilities. The X-33 was no longer the only path to low-cost orbital access. Program delays became a public concern. Milestone dates slipped repeatedly, frustrating NASA administrators and congressional oversight committees. Each failure or delay was heavily scrutinized in hearings and reports. The agency faced mounting pressure to either justify or cancel the project. Technical optimism among engineers began to clash with fiscal realities. While some believed the problems could be solved, others acknowledged that success might never be achieved. Confidence in achieving single-stage-to-orbit capability diminished. The program's future was increasingly uncertain. By 1999, the cumulative challenges, technical, financial, and political, had created a perfect storm. NASA's leadership faced the prospect of continuing a costly and risky program with no guaranteed success. External reviews recommended reassessment of priorities. It became clear that difficult decisions were imminent. The X-33 program was officially canceled later that year. Despite its cancellation, the technology and data collected informed future spacecraft designs. Engineers applied lessons learned to later projects, including reusable rocket concepts. The program's legacy endured, even without a flying operational vehicle. Though the X-33 never reached orbit, its innovations left a lasting imprint on aerospace engineering. Lifting body aerodynamics, composite fuel tanks, and linear Aerospike engines became reference points for future projects. NASA's data helped refine material science and flight software. The program proved that pushing boundaries often produces unexpected benefits. The program also highlighted the challenges of managing high-risk experimental projects. Cutting-edge materials and propulsion systems introduced unprecedented uncertainties. Program managers had to balance ambition with safety, cost, and political scrutiny. These lessons have influenced how NASA approaches experimental spacecraft today. Linear Aerospike technology, though not fully realized in the X-33, informed engine research for decades. The concept of altitude-compensating engines remains attractive for future reusable launch vehicles. Engineers continue to explore similar systems with improved materials and modern computational tools. The X-33 served as a testing ground for ideas ahead of its time. Composite tank failures underscored the importance of rigorous materials testing. Modern reusable spacecraft now benefit from extensive simulation and testing regimes. Lessons from the X-33 prevent repetition of early mistakes. These insights remain a critical part of NASA's experimental program protocols. Despite its cancellation, the X-33 inspired a generation of aerospace engineers. Students and young scientists studied the project as an example of bold innovation. Its ambitious goals pushed the envelope of what was thought possible in spacecraft design. Enthusiasm for reusable launch vehicles traces back to this era. The program also contributed to the culture of iterative design and rapid prototyping. Engineers learned to accept setbacks as part of development, a philosophy evident in modern private aerospace ventures. Concepts trialed in the X-33 inform spacecraft now actively flying or in production. The spirit lives on in today's reusable launch initiatives. Ultimately, the story of the X-33 is both cautionary and inspirational. It demonstrates that even a canceled program can change the trajectory of aerospace engineering. Its ambitious vision, technical achievements, and lessons learned continue to shape the future of space exploration. The X-33 remains a symbol of what could have been, and a foundation for what is yet to come.